Yes?
Okay, that's great. Okay, so the next talk is by Martin Eckstein from University of Hamburg. Let me just mute myself and stop the video. So the stage is yours, Martin. Please go ahead.
Yeah. Okay, yeah. So first of all, of course, thank you for inviting me. And I must say again that I'm really sorry that I'm not in Boston. I was not feeling well at the end of last week, so I decided not to fly. But you can imagine that I really prefer to be in Boston now, having some lobster and some good physics discussions. Yeah. But at least I'm feeling better now, which of course also has the consequence that all the things you want to escape while going to Boston, such as teaching, other local stuff, will come to you anyway. But yeah, but it's great that there's the live stream that I can also watch some of the talks. Yeah. So my talk will be about light matter hybrids. So the central question is can we engineer the coupling of a whole extended solid to vacuum fluctuations of the electromagnetic field in such a way that we can influence ground state or thermodynamic properties of the solid and eventually possibly change phase transitions. So the settings I could have in mind, although this certainly has been discussed in the course of this workshop, it will be discussed, is one possibility is a single mode cavity. I can view this ideally as a resonator, such as a split ring resonator, which supports a single or few modes. The electromagnetic field is confined in a certain mode volume. The vector potential is like one of the displacements of these of the oscillator, and the strength is given by the vacuum field, is scaled by the inverse mode volume. The other setting, which is also quite relevant if you want to go to extended solid, is when you have intrinsically a mode continuum involved. That can be such a coplanar cavity, very similar to the experiment by Daniele, which I guess has been discussed, or also situations in which the electromagnetic field is confined close to interfaces, surfaces, which are so-called surface plus conpolaton modes. In all these settings, what the mechanisms that you can have to discuss to influence solids is either like photon-mediated interactions, where the photon takes the role of the exchange boson, or polarphotonic effects, where like local properties such as tunneling are modified by the coupling to the right, or light matter hybrids, or also non-equilibrium effects, such as when the cavity is used to engineer dissipation or triple cavities. In this talk, I will mainly focus on this first mechanism here, which is long-range interactions, and later say something about this light matter hybrids. So when you think about this cavity quantum materials, one way to start from is to make the analogy to classical light-driven systems. Classical light-driven system meaning that you have an external vector potential from a laser impinging on the solid, which provides a time periodic force. And then you have a light-stressed Hamiltonian, which is the essentially Floquet Hamiltonian of the system. I think this, I don't have to discuss for this audience, it's very well known. I mean, there are many ways to engineer material properties in this way, or many proposals. So to go to the quantum case, one could now just say, okay, let's take this laser and replace this one here by the coupling to a single oscillator mode. Yeah? And in this case, one can get photon-dressed Hamiltonians. Yeah? You can imagine that this cavity is filled already with n photons, and the material now exchanges virtual photons, like absorbs and emits virtual photons with the cavity, and upon eliminating these virtual photons, what you will get is a light-stressed Hamiltonian. Yeah? And here, one now sees the link to the classical case. We would take the number of photons in this cavity to infinity, and at the same time scale down the coupling to the individual photons in such a way that this ratio is constant. Then this photon-dressed Hamiltonian here just becomes the equivalent to the Floquet Hamiltonian. Yeah? So this is a relatively simple mathematical statement. The interesting thing to note is that, okay, I don't know whether this can be seen here, that in this limit Floquet Hamiltonians, or Hamiltonians very similar to Floki Hamiltonians can in many cases be realized already. In principle, you would be able to scale up the coupling sufficiently large with just a few photons in the cavity. And one way to illustrate this is magnetic exchange interactions. And I want to discuss, because I will also discuss magnetic long-range interactions later. So the minimal model here would be a Hubbard model for the solid. So you have electrons tunneling, a local Hubbard interaction. And if this interaction becomes large as compared to the hopping, then the low energy manifold has just spins, and the effective low energy Hamiltonian is a spin Heisenberg model with an antiferromagnetic spin exchange coupling T squared over U, just because it's two hopping pulses to exchange two spins with an intermediate state of energy U. So now if you couple the field to this model, the minimal coupling to this tight binding model is the so-called Payard phase, where kind of the hopping gets a phase that's given by the vector potential projected along the bond, and in the quantum case this works just the same way. So the dimensionless coupling strength here would be the vacuum strength of the vector field vector potential projected along the bond here. And what you can see is that in this case, with each tunneling process, like the electron, the system can emit and absorb an arbitrary number of photons, and as a consequence, kind of this exchange gets pressed in the sense that you can have an arbitrary number of immediate virtual photons. Yeah? And so you have to get the exchange interaction, you have to sum up all these intermediate states. Yeah? So coming from n photons in the cavity, we go into intermediate states with L photons. You have to sum up all these processes. And in the simplest case, like when you start from the empty cavity, you can only kind of re-emit photons, and that leads to a relatively simple reduction of the exchange interactions, because the cavity more or less tends to localize electrons, yeah, and strong coupling. But if you have 1, 2, 3 photons in the cavity, you see that you can selectively, in this case, either enhance or decrease this exchange interaction depending on the frequency of the cavity, whether it's red or blue tuned from the electronic resonance. And what you can also see, if you plot this against the coupling strengths or the rescale coupling strengths, then already with 1 or 2 photons you recover the result which is obtained from the Floki Hamiltonian, so the like classical light-stress exchange. This concept of Floki engineering of magnetic interactions has been used in several other works. One I can mention here, for example, is a nice work by Emil Bullström, also by Unkel, where they used this to engineer magnetic interactions in a frustrated system, and therefore potentially control spin liquid phases. Has been used for like impurity atoms, or also for controlling magnetic charge pseudospins instead of magnetic spins, and therefore controlling the competition between the charge density wave and superconducting. So, but the cavity can do more than basically replacing this Floki engineering, and this more is long-range interactions, which I want to discuss now. So the simplest way of understanding long-range interactions, you have the leading term in the light-matter interaction, which is of the type vector potential type current. Then this leads to a arbitrary long-range interaction of a current type, because two sides in matter exchange a photon, and this interaction, or retarded interaction, is given by the photon property. Yeah? And this is what is, for instance, behind photon-mediated superconductivity that has been discussed by people in this audience, I guess. And so I want to stress that, like in the language of Floki engineering, since I brought this up, Floki engineering's classical types cannot be used to get these long-range interactions. Yeah? This might be a trivial statement, but if you think of a system which is just separated in 2 parts, yeah, so and you provide these 2 parts with one common field, yeah, then also the Floki Hamiltonian will always separate in 2 parts. They will not know something from each other, because the Floki Hamiltonian is a generator of the stroboscopic time evolution, and if you have 2 independent parts, then also the time evolution of these 2 independent parts arises. Yeah? So these long-range interactions always need some kind of quantum boson to be exchanged. So I don't want to discuss here long-range interactions which are due to this linear light matter coupling, but I want to go one step beyond and discuss interactions which rely on a non-linear light matter coupling or 2 or n photon process. Yeah? So you can think that the interaction with matter involves like the scattering of a photon from one mode J to mode I, or kind of the emission or absorption of several photons. Yeah? And as before, you can put this together and say that there is long-range interactions that involve now the exchange of 2 photons, or more than, or even more photons. So why should we be interested in this? Well, one thing is that this naturally can then be used to engineer also long-range interactions which are not of current type, but involve arbitrary other different such as you will see spins. Yeah? The other consequence is that this setting can also be used to change these interactions now by external driving. Yeah? Just you can, in a simple way, put in here, just replace one of these 2 photons by a classical laser drive. So you absorb the photon from the drive, scatter it into the cavity mode, and put it back to the drive. This setting here is precisely the setting that it's in a standard way used to also engineer long-range interactions in synthetic quantum systems, such as cold atoms. Yeah? But here the setting is usually very different. So one has a high finesse cavity and electronic transitions and the laser frequencies which are very well separated, while in solids all these energy scales mix up much more. So it's an interesting question whether there are situations in which one can really use this like laser driving to control long-range interactions in solid. So regarding this part here, that we can do it for general degrees of freedom, let me discuss this also for the magnetic interactions, because what I showed you before is that basically the super exchange, once the system is coupled to light, can involve also the absorption and emission of several photons. So you naturally get an effective light matter Hamiltonian, yeah, which has a spin flip, this operator S.S on a bond, going together with either absorption and emission of a photon or 2 photon absorption and 2 photon emission. Yeah? So if you now have 2 bonds which are arbitrarily far separated, just connected by the photon, you will get like interaction, which is just the square of this process. Yeah? So this can be seen, the square of the process can be understood in like 2 ways. Either you can say this is kind of a like correlated spin flip at 2 distant sites, yeah, which is correlated via the photon. Another way of seeing it is a singlet-singlet interaction, yeah, because this Heisenberg interaction basically distinguishes between a local singlet and a local triplet. Yeah? The triplet doesn't see light, the singlet sees light. Yeah? So in a sense, this interaction here can be also extracted by just taking a system which has 2 such dimers in a cavity, diagonalizing or solving this exactly, like taking into account all photon modes, and evaluating the difference between like the state where you have 2 singlets here versus twice the state where only one of the 2 is in a singlet. Yeah? So this will be the interaction. But this is the other way, is, as I said, is just a correlated spin flip. Yeah? And then you can evaluate this in the vacuum. So for empty cavity, you get some result here as a function of the frequency. You can, I will discuss this later. You can also kind of get it analytically. That's a lot of work because it's a high-order perturbation theory, which was done by a PhD student, Paul Fadler here. And what you will see that this interaction, of course, the leading order is 4th order in the hopping. You need like 4 hoppings to make this exchange. Yeah? And then it depends on the coupling strength to the cavity and on the frequency of the cavity. Yeah? So now the question is, would you expect this to be relevant at all? Yeah, since actually, in particular, in the untriven case, when you have only vacuum fluctuations. Yeah? Because vacuum fluctuations are anyway small, and now you want to have nonlinear processes being driven by vacuum fluctuations. So you might expect that this is irrelevant, but you can pitch in some numbers. Now for a typical mod insulator, this is like Hubbard interaction of 1 eV, a small hopping, rather representative of organic mod insulators, typical lattice spacing of a nanometer. I take a cavity, terahertz cavity, with a mode volume that I take as the control parameter. Yeah? And now we have the coupling strength, which is this dimensionless coupling appearing in the Payet space, so kind of the vacuum flat field projected along the front. And this, of course, goes down with the cavity, with the size of the cavity here. Yeah? If you go to a micrometer volume, which still corresponds to a huge mode compression as compared to the free space wavelength, you still have this parameter to be very small, which in particular means that these floquet-like effects are all absent in this case, yeah, or would be negligibly small. Now, if you look at these long-range interactions and you want to compare the strength of this long-range interaction compared to the other relevant interaction, which is the short-range chain, you have to also take into account the fact that this long-range interaction connects all bonds in the system. So if you would fill up your cavity, you have n bonds in the system. So the relevant interaction to be compared is kind of a mean field interaction, which is the individual interaction times n. And this is also plotted here, yeah, as a function of the cavity size. And what you note immediately is that also this goes down for a large cavity, which is understood because if you have a large cavity, then this individual thing here needs 4 photon processes, those proportional to scales is the coupling strength to the power of 4, which is 1 of the volume to the power square. Yeah? When you multiply this with the number of particles, it still goes down with 1 over the volume. So this is very much in line with the usual story. It's very hard to use a single mode cavity to influence a matter in the thermodynamic limit. On the other hand, if you really look at the numbers, at the quantitative numbers here, then you find that for cavities which are still large enough to host, we put it in 10 to the 3 or 10 to the 9, so almost macroscopic number of atoms, and call this some mesoscopic size, then you come to a regime where this interaction, long-range interaction, can actually dominate the original short-range exchange interaction. Yeah? So these interactions are really, in this mesoscopic limit, quite important, I would say. Okay, so one can also use driving here. Let me be a bit fast because I want to be also, I want to have time for the last part. In the driven case, you can add an external laser to the cavity. Now you have both the laser and the photons here, and then you can also eliminate all the laser processes and the photons, and you get a rich map of depending on the cavity frequency and the laser frequency of these long-range interactions. One finds a resonant enhancement when the driving frequency is resonant to electronic transitions. That's expected, but of course these are masked usually by in the solid by huge absorption bands. But you also find resonant enhancement when the laser driving is resonant to the cavity. Yeah. Let me skip to this. And this would be Floquet engineering of the long-range interaction in this case. There's one comment I want to make about the derivation of these interactions, which I find worthwhile to make, and which has cost also, I guess, us some time. So the naive or straightforward way to understand these interactions would be that we say, okay, I construct first an effective Hamiltonian that describes this nonlinear light matter interaction. Yeah? So kind of a sketch thing from a state I to a state F in the solid near when the laser and cavity photons are exchanged. Yeah? And the matrix element of this you can obtain, and then you basically do a second order perturbation theory in this effective Hamiltonian to get the long-range interaction. For the spin interaction that I have discussed, that would, in the vacuum-mediated spin interactions, that would mean that I get the effective matrix element for a spin flip upon the emission or absorption of 2 photons, and then I would eliminate the photons to get the effective interaction to form this effective matrix element squared with an energy denominator which is just 2 times the photon energy, so the 2 times the virtual photon energy. And if you do this, you will get the following result. So the exact result would be the black line, while the result from this spin photon Hamiltonian, I would say, is the red line here, which is entirely different. In particular, it has suggests the resonant enhancement of the interaction whenever the cavity frequency is resonant to electronic transition, which is completely absent in the exact result. And this fake resonances, I would say, just comes from, one can understand it in the following. This nonlinear light matter interaction, of course, involves intermediate electronic states, such as these charge excitations. And when you put together your full photon-mediated interaction, it is essential that you treat like the intermediate virtual photon states and the intermediate charge states really on the same footing. Otherwise, you get the wrong result, and these divergences really come from a cancellation of all these different states. So this is important to keep in mind. The only case where basically this spin photon approach would hold is the case where you really drive close in resonance to the cavity. Because in this case, the dominant intermediate state, or smallest intermediate state energy, would be one in which you just have exchanged the cavity photon and the laser photon. Yeah? And this is also the regime in which cold atoms work when you engineer long-range interactions. However, in solids, where you have like dissipative modes and bad cavities, I guess you can never go close to resonance and as close enough to resonance. And okay, view of time, let me skip over this, but if you would go to this organic system which I just had, and you assume that you want to achieve by driving strong long-range interactions, and you want to do this by just 10% off resonance driving, you see that you have to, this spin photon approach would not be done. So let me just summarize this part. In the first part of this talk, I have discussed like nonlinear interactions. Interactions come from nonlinear light matter interaction, can be used to control magnetism, but similar things can also be transferred then to control orbital exchange and other type of exchange interactions. That's to be done. And what I find remarkable that is in the mesoscopic limit, really these interactions and even the vacuum-mediated one can dominate over the short-range exchange interaction, can therefore be relevant. And what we'll also do is then in future is, I mean, one should take this Trimpton case and also, in this case, replace the single-mode cavity by some like dispersive cavity modes or plasmon modes, because in this way one can use the same formalism to predict correctly the long-range interactions that have a spatial structure and arise from the domain. And the other comment that I made here was this failure of the effective Hamiltonian approach, because in the solid state setting it's hard to have situations in which you have very sharp, very closely defined resonance conditions. And this is really a work done by a PhD student in Erlangen. Paul Sadler has done an enormous work, in particular the work regarding all these fourth-order perturbation theory type conditions. With this, I would use the last minutes to come to the second part, light-matter hybrids. This is a completely different story. And so light-matter hybrids have been discussed a lot in the context of second-order phase transition, where, for instance, in ferroelectrics, the cavity hybridizes with ferroelectric modes and therefore leads to a condensation or change of the condensation of these ferroelectric modes and the change of ferroelectric transitions. Here, I want to not discuss this and rather ask whether we can also use this light-matter hybrids to control first-order phase transitions. This is very much motivated, of course, by experiment by Dan Wiegele, which has been discussed in this workshop before, so I can be very brief here. This, from my simplifying perspective, basically it takes a metal in a cavity, this material has a first order metal insulator transition with a nice hysteresis as a function of temperature. And if you put it in the cavity, you simply completely shift this phase transition by tens of degrees of Kelvin, and this is changed both by changing the cavity resonance frequency, but also by changing kind of the tilting the willows, which presumably changes the quality factor of the cavity. Yeah. So there's two possible explanations that are being discussed in this work. One of them would be just this light matter light scenario, or is also a selective Casimir effect. And the story works like this: if you have a first order transition from insulator to metal, that means here in the low temperature phase, the free energy of the insulator is lower, and in the high temperature phase, the free energy of the metal is lower. Yeah? Now, due to the hybridization with the light, when these free energies will change, and this change will be different for the two phases. So, for instance, you can assume that predominantly the metal actually sees the electromagnetic field, therefore the free energy is lowered, and the phase transition is shifted. Yeah? So this is a nice mechanism. However, of course, it's supposed to be very small. Like in this paper, there's a phenomenological estimate, more or less, of the free energy change per mode, which you can get. And this can be rather large, but then the thing which kills you is that the number of modes, which is relevant here, is relatively small, because the cavity changes only a small phase space of modes. Yeah? And this means that this effect is presumably orders of magnitude too small, and there's an alternative scenario which is more based on the Purcell effect, which is much more likely to work, and which I guess has been also discussed by Daniele. I actually didn't listen to the talk by Daniele because it was too late in the evening, so I don't know what you have said. Yeah. Anyway, here I want to still elaborate more on this free energy scenario, more in a microscopic setting, and also check when it can work and when it can be made work. This is work in progress, so nevertheless, I wanted to share this with you. So here we want to look at a microscopic calculation for first order metal insulator transition, and this is obtained again in the Hubbard model. Yeah, so at least in high dimensions, where you can solve it with dynamical mean field theory, you find a first order metal insulator transition. It's a function of the interaction, yeah, which at high temperature turns into a crossover. And it is very much reminiscent also of the first order metal insulator transition, which you get in some correlated materials like organics, also transition metal oxides and others. So the essence of this first order transition is like we have this transition line here. If we would analyze now the spectral function here, okay, this then in the metallic phase you have, it should be omega 0. This is the electronic spectral function. You have some kind of narrow peak here, which corresponds to a band of denormalized quasiparticles, and kind of high energy spectral features which correspond to the so-called Hubbard bands. And then if you come closer to the transition, this quasi-particle band gets stronger and more normalized, until at the transition itself there is a discontinuous change now, where you reduce the spectral wave at the Fermi energy. This is some kind of real set of data here for the DMFT solution for a 2D square lattice, and this is kind of a proxy, at least for the spectral wave at the Fermi energy, which you see changes discontinuously. Another quantity which changes discontinuously is the W occupancy, the number of W occupied site, which also is reduced in the insulator. So now we want to couple light here, and the way to couple light is we have to couple now, in this case, a continuum of modes, because we have this extended cavity, but it still works via the Piers substitution. Basically, the Piers phase now, the vector potential on the bond, and the vector potential now has to be expanded in its modes. Yeah? The modes which have transverse propagating momentum and some mode function in the perpendicular direction.
Martin, do you hear me?
So, yeah.
Just just want to say that since we started a bit later, you still have 10 minutes, but just keep time in mind, okay?
Yeah,
10 minutes including
I know.
discussion.
Maybe just 3 more minutes or so, and
Yes,
then
yes.
we can
Of
go
course,
to discussion. Is that okay?
Yeah. Take 5 more minutes and then we can go to discussion. Thank you.
Okay. So, yeah. So what we want to do in future is, of course, to fully consistently solve this model here within this dynamical mean heat theory. Now we are not yet here, but what I can show you is basically the manifestation of this free energy model. Yeah. So the free energy as a function of the interaction U here, of course, you can analyze this close to the metal insulator transition. Yeah. And so the change of the free energy with the interaction is just the double occupancy. So you see that in low U, the metal is the leading phase. At a large U, it's the insulator. And the metal, of course, has a larger double occupancy at a larger slope. And as before, we now expect that the cavity kind of renormalizes the free energy of these two phases. Okay, and this is different for the two phases. So this leads to a change of the metal insulator transition. And if you just take this linearized picture here, you can immediately see that the change of the metal insulator transition is just the ratio of the change of the free energy with respect due to the light matter coupling over this difference in the double occupancy. So now what we can do is we can calculate this change of the energy. Well, it would be something like this, which looks like awkward, but what it is nothing else than the free energy change, which you would get for the hybridization of a bosonic mode with other bosonic modes in the material, and the spectrum of these bosonic modes in the material is just a spectrum of possible transitions, electronic transitions from K to K plus Q, where Q is the momentum of the boson, and energy omega plus Q. Yeah? And this spectrum, as you can already guess from this one here, will also change discontinuously, because in the insulator, you will get out the low energy part of this spectrum. Yeah? And since I'm short in time, let me just skip over the data and show this. Now, question, what is the model for light, which we should take here? If I would take a coplanar cavity, yeah, I could evaluate this change as it is for like one of these cavity modes. But of course, as I said before, I should take into account only the modes up to a momentum where the cavity has an effect. Yeah? And this momentum here is of the order of the distance here, yeah? This cutoff momentum, which means that the number of modes which enter this sum here scales with this cutoff over the size of the Primar zone, or in other words, the lattice constant over the free space of the wavelength here, which is a very small factor. So this will not work. Yeah? You have to find a way to couple an extended kind of phase space of modes to the solid, and one way to do this is to use this surface plasmon modes, because these are modes located close to a surface. They have a flat dispersion at large Q, at large momentum, and basically they are localized close to the surface, and the localization is controlled by the distance. By the wave vector. So the larger the wave vector, the stronger they are localized at the surface. So what you can do is you can put the material in a certain distance here, yeah, and the coupling, the distance to the interface, will actually control the extent of momentum space over which you couple the material to this surface cluster. And with this, you can now basically go ahead and in this metal insulator transition evaluate the free energy change. Let me just be quick here as a function of the basically plasmon frequency which we can choose. You can evaluate this, and as you basically put the material closer and closer to the surface, to the interface here, this free energy change goes up. The order of magnitude seems small, but you also see that in order to get the change of the phase transition, you have to compare this to the slopes of the free energy curves, which is the distance in difference in W occupancy, which is also small, which really suggests that for these realistic parameters, you can really control the metal insulator transition by large amount by just bringing the material closer or more distance from the interface. So this ends this part. Since the time is short, most important thing is to acknowledge that the people, like the second part is the PhD thesis of Katharina Lenk, and of course the discussion which goes in here is very much also with Daniele Pauzzi and the other, his group on these mechanisms. The first part was the hard work of Paul Fadler. And with this I thank you for your attention. Once again, I'm sorry that I'm not there, and open for questions.
Thanks a lot for the very nice talk, Martin. So, are there questions? I think who was first? Let's pass it to Mohammed and then we'll
Hi Martin, I hope you're doing well. The question was about the formalism. So you use pi substitution, and there is that G in it. And then I was wondering to what extent one can assume G to be large and the pi substitution is still valid. And the reason is that, well, we know that if we expand it, we just get like higher orders of A, and they're unphysical, and we have to include more bands. So is there like a rule of thumb that I should know to what extent I should assume G to be small? Thanks.
Mm-hmm.
I think he heard
I didn't hear everything, but as I understood, the question was to what extent I can assume the pi substitution to be correct if G becomes large.
Exactly. Yeah.
And I think this is a very valid question, of course, and because what the pi substitution, in a way that I've written, what is the main approximation behind this pi substitution is that I assume that in this representation, where I use the pi substitution, the bands are very, so the interband dipolar couplings are not relevant. Yeah? And this is the main question, whether dipolar couplings to other bands have to be taken into account. Like this would be the first correction. Yeah? Yeah. So this, of course, also depends on the type of like the band structure and where your other bands are and how large the dipolar couplings are to these other bands. But this would be the first correction, I guess. Yeah. Now for these two second parts, I think the individual mode coupling, yeah, is always small. Yeah. So this G basically for an individual mode or individual plasmon mode to the solid would be relatively small. So here I think it's relatively safe. In this like single mode cavity where you really go to a strong single particle coupling, I don't know. You know, so there's definitely at some point have to take into account higher bands.
Hello. So my question is actually about screening, because, for example, in all plasmonic structures and like surface plasmons, there are essentially longitudinal fluctuations. Can you hear me? Hello?
Yeah.
So in plasmonic structures and like surface plasmons, there are essentially longitudinal fluctuations of electromagnetic fields, which means that it's going to be like a screened very efficiently. For example, if you couple to some conducting material. So it means that the effective interaction strength should kind of be decreased due to this effect.
Mm-hmm. Yeah, that's a good point, and I think this comes on top. Yeah. So if I now really would go back here, if I really think like now in this setting here, bring now my material close to a metallic surface, then this will also change screen the longitudinal part of the electromagnetic field, which is on top of this transverse field, which I discuss here. And this will in particular be important if I have long-range interactions in the material. Yeah? So here I was now discussing something where I was assuming that the material itself is well described by some Hubbard models, so I have already neglected the short-range, the long-range interactions due to kind of internal screening in the material. And if that's valid, then also the effect of screening on the short-range interaction from this metallic part here will be smaller. However, it will not be negligible. So if you want to have a quantitative prediction how the metal insulator transition changes, you will always have to consider both of these effects. That's completely true.
Is there maybe a last question for somebody? I don't see any hands, so let's thank Martin for this talk. So now we continue with the coffee break and see you back. We start at 10:20.
Dimmi un po' di bellissimo. Abbiamo fatto